So we're going to conclude our unit about organic chemistry with 3 short videos. This is the first one, and is about the nomenclature of organic compounds. That can be quite complicated, but we are just going to say simple, and we are focusing on hydrocarbon, adding just something about double bonds and triple bonds. And so the good thing is by the end of it, you will be able to actually understand the joke. In last week's video, you learned the names of the first 10 alkanes. Hydrocarbon are the constituent of petroleum and natural gas, so they're obviously economically very important, even if these days the price has gone pretty low. And they obviously they are interesting in terms of fuel, so they are very flammable, and they are interesting in terms of being precursor of several chemical compounds, but per se they are pretty inert. So other than burning, they don't really react much. The bond between carbon and hydrogen is quite stable, and basically there is no functional group. So other compounds that you may relate to this, it's paraffin, that is a mixture of solid alkanes with a number of carbon between 20 and 40, and is what candles are made of these days, although historically they were using different materials. But so obviously they burn well, but you know, they also preserve very well. If you remember when I brought the sodium into the classroom, or whatever other teacher you had in Gen 1, and we put it into water, and we saw that very potassium, sodium, and lithium, we saw a very vigorous reaction. We mentioned the fact that those metals are so reactive that they need to be stored under mineral oil, because mineral oil is very inert, and that's also a mixture of alkanes. So the thing is, though, that whenever you are trying to give a name to a compound that may be quite complicated and have a lot of functional groups, the very first thing you need to do is to figure out the backbone, and that's going to determine the general name based on the name of the alkane that share the same backbone, basically. So they are kind of the corner point for nomenclature. So I'm assuming that you remember those names. So let's have a look at these two structures. If we count the atom of carbons, for both of them we have 5 carbons. So they have the same formula, that is C5H12. This corresponds to CnH2n plus 2, because there is no cyclic structure, there are no double bonds, no triple bonds, so this is they're both alkane, but they're obviously different. If you would go and measure their, for example, the melting point, you will find 2 different numbers. So they have different physical properties because the shape of the molecule is different, and this molecule having just a little refreshing of Gen 1. The main intermolecular forces here are a temporary dipole, like London forces, so they depend on the molar mass, but obviously here you have the same molar mass, you have the same number of electrons, but they also depend on the shape of the molecule. So for this molecule on this side being more linear, and this one being somehow more globular, for this one you have more surface respect to the volume of the molecule, and therefore there are more interactions, so that the London forces are a bit stronger. Well, here the intermolecular forces would be a little be weaker, not a huge difference, but enough to give you 2 different melting points. So this would have a larger tendency to be solid than this, right? So, but closing that excursion in Gen 1, we need 2 different names because these are 2 different substances. So we are going to look for the longest chain, right? So in this case, obviously, it's kind of useful to draw a bubble around the longest chain and to see what's left out. So imagine you are a little subatomic person, and you're walking through that path inside the bubble, so to speak. So basically, you could go through all 5 atoms of carbons without ever having to go twice on the same carbon. So you can go through a path of 5 carbons without finding any intersection. While here, if I take my pen, the longest path is actually only 4, right? So if I start from this side of the molecule and I go 1, 2, 3, I have to make a choice. Either I go down, and that would be 4, or I go left, and it will still be 4. The only way I could go through all 5 would be to go twice over this carbon, right? So if I go all the way here and then I come back, but I'm already been going through this carbon, so that's not allowed. So it has to be, you know, an interrupted path. So no matter where you start, you can try and have fun and start from all the 3 corners of the molecule, 1, 2, 3. It doesn't matter. You are going to have on the longest chain is going to be 4. So for this one, we are going to use the name as a starting point. We're going to use the root from the name of the hydrocarbon that has 4, of the alkane that has 4 carbons, that's butane. While for this, we're going to use the name pent from pentane. This here, that's been left out of my bubble, is going to be a branch. So I will have to find a name for the branch, and I also have to tell you where the branch is connected to. So it's like a street address. There has to be a house number. And to do that, I need to number the atom of carbons, and that can be done. So you need to start from one extremity, and you may think that you can see easily that there are 2 different options, right? If I start from here, my branch is on the second carbon. If I use a different color and I start from here, my branch would be attached to the 3rd carbon. So in instances like this, where you have 2 potential numeration, you have always to pick the smallest, the numeration that gives the smallest number in the formula. So these are the 2 skeletal formula, and they are slightly more realistic in terms of shape, because in these drawings, there appears to be 90 degrees angle between carbon and hydrogen, or here between carbon and carbon, but that's not true. Those are all those carbons are sp3 hybridized sp3. Therefore, they have a tetrahedral shape, and the angle is 109.5. In this skeletal formula, the angle is 120, so it's still not realistic, but somehow it gives you the sense of a zigzag structure, and well, you can see that this one is a little bit more compact, kind of more globular. Okay, so as far as names go, we need to give a name to the branch, right? So the branch shows some similarity with methane, right? If you think about methane here, the branch looks like a methane that has lost 1 hydrogen and has used that opening to make a connection with the main chain. So because this was methane, this branch is taking the name from meth, and then we are adding -yle, so it's going to be methyl. So these are the 2 names for the substances, pentane and 2-methyl-butane. You may also, so that would be, let's say, the proper name according to the rules. The rules are called the UPAC or EUPAC rules, and so there is a committee that decides about, you know, so that we all stick to the same convention. But then there are normal names, right? It's like, for example, water, you don't call water dihydrogen oxide. Or you know, ammonia. So we have those common names, and what happens is that for some hydrocarbon there are common names, and the common name for this is isopentane, because it's kind of look like pentane, right? So it you know, before this decision about naming were made, it seemed logical, because the total number of carbon at the end of the day, there were 5 carbons total, to have a name that was similar to pentane. but the proper name will be 2-methylbutane. So which name do you need to know? You only need to know the names according to the rule. So for this compound, you will only have to be able to tell me that this is 2-methylbutane. If you don't remember that it's also called isopentane, it doesn't matter, basically. The 3 formula down, right? Would you say those are the same thing, or those are 3 different formulas? This can be hard at the beginning to figure out, but because the way we draw them is arbitrary, and I can decide to make a turn wherever I want, basically. Also depending, like here, for example, I'm running towards the edge of the page, and I have no room anymore, so I go down instead of going straight. But you always have to think to how would you name them. If the name is going to be the same, it's going to be the same molecule, right? So let's see which one is the longest chain. So here I could go straight, and I see a chain of 4, and then I have a branch. Here I also have a chain of 4 with a branch, and here I have a chain of 4. If I go down here with a branch, I kind of flip the color, but it doesn't really matter. And in all instances, the longest chain is butane, right? And then there is a methyl, and the methyl is in 2, because if I start numbering from another hand and I get 3, that's not according to the rule. Does 3-methylbutane even exist? Let's try to draw it, okay? Carbon 1, carbon 2, carbon 3, and carbon 4. I connect them. I left out the hydrogen because I'm a bit lazy today, and I want the formula to stay simple, but there will be enough hydrogen to fill all 4 bonds for each carbon. So 3 at the 2 extremities, 2 here, unless I put a branch, in which case there is room only for 1 hydrogen. So if I want to put the branch in 3, I would have 1, carbon 2, carbon 3, so I have to put it here, right? But then, according to the rule, when I name it, I would have to start from this carbon. That's carbon 1, because starting from here, I can ensure that the number where I put the branch is actually going to be not 3, but 2. So 3-methylbutane does not exist. That in other words, if you're trying to put together a molecule that is a chain of 4 and a branch of 1, there is only one way to do it, basically. So this slide is showing you how to derive the name of the branch from the alkane. So for example, if you have a branch of just one atom of carbon, so then the branch is thought as derived from methane, right? So you take the root meth and you add this suffix YL, so you get methyl, ethyl, propyl, butyl, pentyl, and so forth. Let's work on some example because that will make things a little bit clearer. Let's see some examples of naming. So this first structure, the first thing I want to do is identify the longest chain. So I'm going to highlight the chain in yellow. 1, 2, 3, 4, 5, 6. So the longest chain that I can find is 6, and it doesn't matter where you start, you cannot find anything longer than 6. So the first piece of the name we can put down is hexane, because that's the hex is the root for a chain of 6, and ANE is the suffix for chain of carbon without double bond, without triple bond, without a cyclic structure. Okay. So now, what can we say about branches? We can see that there are 2 branches, 1 and 2. They both consist of just 1 atom of carbon, so the name of the branch is methyl, and they are in 2 different positions. So in order to give the address, so to speak, to the location of those branches, well, first of all, I want to tell that there are 2, so I need to add another piece another prefix, that's di, so dimethyl hexane. But then I need to give the location of those two branches. So I need to number so that the branches have the lowest possible number. So for that, I'm going to start from here. So that's going to be 1, that's going to be 2, and that's going to be 3, and so forth. But I don't really care about writing the other numbers because there's really nothing there. But just because it's the first example, let's do it. Okay. Okay. So the first methyl is in 2, the second methyl is in 3. And I'm going to write it like that. So the two locations are going to write close to each other, separated by a comma. So between two numbers you always have a comma. Between a number and a letter you have a dash. And note that there are no empty space, no blanks, no spaces. Now it doesn't really matter in this context because you're going to have a multiple choice. So you just pick the names that you pick one name or the other, but they are already written for you. But if you will have to take organic, you will have to learn. You may have like short answer in the test and so forth. So let's have a look at the second structure. So again, I'm going to take my highlighter and figure the longest chain. That's 1, 2, 3, 4, 5, 6. So I have again a chain of 6, so it's again hexane. Now I'm going to put the number so that the branches are in the smallest, have the smallest number possible. Okay. The branches are again 2 methyl, but the difference this time is the, oh, I didn't want black, but that's okay. The branches are kind of connected to the same atom of carbon, right? So because each carbon can only make 4 bonds, that means that the carbon that's here in the middle, this carbon here, does not have any hydrogen connected to it. So it's very similar to before, but this time I will have two identical numbers. Okay, so it can be confusing because you end up with 3 times the number 2, but those number 2s are telling you different things. So this one, written as figures, are telling you the 2 locations that this time they happen to be the same, where the 2 methyl are connected. This one, that's the number 2 as a prefix, is telling you that you have 2 methyl groups. So that's for this structure. Let's see some other example. So here we have another example. Again, we want to find the longest chain. So let's say I start from here. It doesn't really matter where you start, you should always end up with the same. So 1 and 2, 3, 4. Now here I could go up or I could go down, but it doesn't really matter. I still get 6, right? So I have the main chain is hexane. Now I'm going to have a look at the branch. The branch has 2 atoms of carbon, so it's ethyl. And then I need to give the position, so I'm going to number starting from the left, because this way the branch happens to be in 3. If I start from the right, the branch will be in 4, and I want the smallest number. And that's a name. Let's see another example. So the main chain here is going to be 1, 2, 3. Now if I go down, it's going to be 4 and 5. If I go right, it's going to be 1, 2, 3, 4. If I go down, it's going to be 6, so hexane. If I go up, it's going to be hexane. So pretty much every possible turn that I take, I always end up with a chain of 6. So this is also going to be hexane. The 2 branches are a branch of 2 ethyl and a branch of 1 methyl. So the methyl, I'm going to start counting from the right, because I want the branches to have the smallest possible number. So it's going to be 1, 2, 3. So it's going to be the methyl is in 2 and the ethyl is in 3. Now, when I write them down before hexane, I need to make a decision about which one goes first. Okay, so they're going to go in alphabetical order, and when you are considering the alphabetical order, you do not care about the number 2 and the number 3. So all I care is methyl as an M, ethyl as an E, so ethyl comes first. So it's going to be 3-ethyl, 2-methyl hexane. It's a bit like putting back the books on the shelf of the library. Right? There are all those rules and it take a while, but eventually, then you, when you get proficient, you go into automatic pilot. Let's see a new example. This looks quite overwhelming, right? So let's just go with the usual approach. Let's find the longest chain. So I'm going to start from here. So 1, 2, 3. I'm pretty confident that if I stop here, it's going to be pretty short. So let's just keep going. 1, 2, 3, 4. Now down here, if I go down here, I will get 6, but it looks like there is more way to go if I keep going towards the right. So 1, 2, 3, 4, 5, and then I start going down 6, 7, and 8. So I can build a path of 8. So let's circle out everything that's outside that chain that's going to constitute a branch. So I have a methyl here, I have another methyl here, and another methyl here, and then I have a methyl here, and then I have a ethyl here. So I have 5 branches attached to the main chain. So I'm using the as a main part of the naming octane, right? So oct tells me there are 8 atoms of carbon. Ane tells me well, this is a saturated hydrocarbon. That means no double bonds, no triple bonds, no cycles. I have as many hydrogen as I could possibly fit in a carbonic structure. That's where the word saturated is coming from. Because every introduction of double bonds, triple bonds, or cycles would just take down the number of hydrogen. So but potentially you could break those double bonds and add more hydrogen, right? So the process of saturating a compound, that means to transform it into an alkane, is going to be called hydrogenation. And this may ring a bell because you have heard of saturated fats, hydrogenated fats, right? So now we have to put the branches. So we have we have ethyl and we have methyl. So the ethyl we have only 1, the methyl we have 4 of them, so it's going to be tetramethyl. And then we need to give the position. So we want to number this so that the branches get the lowest number. If I'm starting, let me get the pointer. If I start down here, the first branch would be here, it would be 1, 2, 3, 4, 5. If instead I start here, I will get the first branch in 2. So that seems the way to go. So I'm going to start 1, 2, 3, 4, 5. Nothing attached to 5. I'm going on the other side because there's no room. 6, 7, and 8. All the branches are now on 2, 3, or 4. So for ethyl I have only 1 and it's in 4. For methyl I have 2, position 2, and then I have position 3 twice, so it's going to be 2, 3, 3, and then the last one is in position 4. So I'm going to write all those numbers, repeated as many times as necessary, separated by commas. At this point I can put them together, and I know that I need to go in alphabetical order. So for ethyl comes before the tetramethyl. Potentially you may come up, so I would say the most common mistake that could happen if this would be a question in an exam is that you do the numeration starting from the wrong point. So you start numbering from the bottom, right? In which case, so the one that I was telling you before, so in which case you would come up with that the first branch is in 5, and so that would be the answer. And because it's a multiple choice, it's very likely that that would be one of the wrong answers, right? So there is a sort of a urban legend, if you look on the internet, that the way you decide which one of the two is the correct one is by adding up all the locators, so all the numbers that are in as an actual figure, all the position basically, and see which one gives you the lowest. So for example, for the top you would have 4 plus 2 6 plus 3 9 plus another 3 is 12 plus 4 is 16, as opposed to the one below where you in black that you would have 5 and 5 10, 6 and 6 12, so it's 22, and then 29. So people would say, see, the right one was the one with the lowest sum, right? So although that's going to happen often, it's not going to happen all the time. Therefore, that's not a reliable way to decide, right? So imagine yourself, you are answering a multiple choice. There are several choices. You cannot figure out. You have restricted you have eliminated 2 because they were obvious mistake, and now you have to decide between these 2. That obviously differ only because one started numbering from the right and the other one was starting the numbers from the left. So what do? Do not sum up the numbers, because although it might often works, it will not always work. So it's only a matter of time it's going to drive you into a mistake. The proper way is to look for the first number between the two names in which there is a difference, right? In this case is immediately. Let me get the pointer. Okay, so the first number, you're going through the numbers, and by numbers I mean the actual figures, so like 4 2 3 3 4 and 5 5 6 6 7, and you want to identify the first moment where the two numbers are different between the two formulas. And here it happens right away. The formula, the naming on the top as a 4, the naming at the bottom as a 5. Okay, so when you stop and you think which one is the lowest, it's 4, so 4 is the right name. So beside anything else, beside the fact that this is always going to give you the right answer, this approach is also much faster than the other one. So let's see this structure. There's a nice symmetrical shape like a plus sign. So the first thing we want to identify the main chain, and I might as well go horizontal just to make my life easier. No matter how you try, the longest chain you can come up with is a chain of 3, so this would be propane. And then you can see that there are 2 branches made of just 1 atom of carbon, so methyl and methyl, both in the central position. So again, due to the symmetry, it doesn't really matter where I stand counting, the central position is going to be 2. So it's going to be, there are going to be 2 methyl, so it's dimethyl, and it's 2,2-dimethyl propane. Now let's have a look. The thing is, this is as a nickname, so it's one of these structures that have a common name, and the common name is neopentane. And now again, you don't have to worry about that. When I ask you for this test, I just refer to the UPAC name, not to the special names. This structure here, that's a bit more complicated. It's kind of a symmetrical sort of structure. So the longest chain, if I start counting from the bottom, 1, 2, 3. Now I could go left, I could go right, it's not going to make any difference. And then I go here, and then again I could go up, down, or right. Doesn't make any difference. The longest chain is 1, 2, 3, 4, 5, 6. So this is hexane. And then I'm looking to the branches. So I have 1 methyl here, 1 methyl here. And now here I have quite a complicated branch because it's made of 2 atoms of carbons, 1 and 2, Obviously, I don't count the one in the intersection because that's already the atom of carbon for the yellow chain, right? So let's put numbers so it makes easy. So I want to start from here so that the first two branches are going to have the smallest possible number. That would not be the case if I would start from the bottom of the molecule. So this is carbon number 3. Now, in 3, I have 2, those little blue dots, carbon, so I have an ethyl, but the ethyl in turn has 2, let's say, secondary branches attached, 1 and 2, and those are methyl, right? So I have 2, let me get the pointer, 2 methyl connected in position 2. So we have learned how to name that part, but we have an ethyl that has sub-branches in position 3. Okay, so the ethyl in the position 3, but then I left some room because I want to tell that on the first atom of the ethyl there's going to be 2 methyl. So how am I going? I need numbers for that too. I'm going to you start from, let's say, the close to the connection, and you go away, increasing the numbers. You may also want to add an apex so that I know that this is different. This one is different from the other one, and the 2 is different from the other 2, right? So in position 1 with an apex, I have 2 methyl. So I'm going to put that in parentheses. So I know that there is a sort of a subordination. Okay. And that's going to come first alphabetically, then this. When you alphabetize, you don't count the numbers, nor you count the di, tri, penta, tetra, you name it. You count the actual name of the branch in terms of you look at that for the alphabetization. So it's kind of a lot, and it's kind of a it gets a bit too complicated. So you may find for this, okay, this is the correct name according to the UPAC. But sometimes there are sort of nicknames, common names. So this particular branch, right, this as a whole with these sub-branches, is called terbutane because it's made of 4 atoms of carbon, right? Let's get the pointer again. So this branch is 1, 2, 3, 4. There are 4 atoms of carbon. So it's called ter, from the word tertiary, butyl. So you can find as an alternate name 3-terbutyl 2,2-dimethylhexane. So meaning that in position 3 you have this terbutyl. So this is a table where you see some the names of some branches that has some sort of common name, so that you don't have to use the parentheses basically. And so you see isobutyl, isopropyl, sec-butyl. Now those terms refers to the fact that the carbon can be is a primary carbon when it's connected only to 2 carbons. It's a secondary carbon when it's connected to 3, and is a tertiary carbon when it's connected with 4, so there is no hydrogen basically. Do you have to remember this table for this exam? No, I just put it there for the benefit of those who knows that eventually they need to take organic chemistry. There's a certain level of memorization. The sooner you start, the less challenging it is. Let's see a last example. First thing, we want to find the longest chain. So let's take a highlighter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we know that this is going to be like decane. And then we need to pick the side from which we want to start numbering. So we have 2 options, right? So the one on the left start on the left, and the one on the right starts on the right. So which one are we going to pick? So the proper way to pick that is to look which of the two would have the smallest number at the first branch. So in this case, the first branch would encounter right at carbon number 2, while here the first branch would be encountered at carbon number 3. So I'm going for the option of the right. If you would be using that funny rule that's on the internet to sum up, in this case, it would get you to the wrong conclusion, because the 3 locands are going to be 3, 4, and 9, while here are going to be 8, 7, and 2. So when I sum them up, I actually get a lower value for the option on the right, but the option on the for the option on the left, 16. But that option is incorrect. Okay, so this is the proper name for this one. Now let's see what, very briefly, how to name alkenes. Okay, it's kind of easy, because basically what you're going to use is the suffix that's already embedded in the name. So if you remember alkenes, you remember the suffix. So let's say this example. Okay, so we want to start the enumeration so that the double bonds has the lowest possible number. Now the double bond encompasses 2 carbons. So am I going to use 1 or am I going to use 2? It doesn't make any difference. We just use, we don't need to specify both. If we are saying where it starts, it can only end at the next number. So we're going to use the first number of the double bonds, the lowest, to indicate the double bond. So the longest chain is a chain of 6, so the root is hexane. We are going to add the suffix for the double bonds, that ene, so it's going to be hexene. And then we need to specify the position of the double bond, and we write 1 hexene. Sometimes you may find, let me get the black, a different order, X dash 1 dash in. Doesn't really matter. It's a multiple choice, so you don't have to write anything really. In this case, you have double bonds and branch, right? So here you see that if you would have started from here, so let's write it here right. If you would have numbered this one 1, the branch would have had a lower number, 3. But so there's sort of a conflict. Which one am I? I cannot minimize both. So either I put a small number for the double bond, but then the branch is going to have a high number, or I put a smaller number for the branch, but then the double bond is going to have a high number. So which one has the precedence? So the most important one is the double bond. So you want to number so that the double bond gets the lowest number, and then you know to bet for the branches basically. So on the other side, you see again that if I would have started from here, 1, 2, 3, the branch would have been having a lower number, but then the double bond would have had a higher number. So that's basically it. Alkynes are compounds characterized by the presence of a triple bond. So remember that these 3 parallel lines indicates a triple bond between 2 atoms of carbon, so you have an atom of carbons at each ending of the triple line. In other words, when you're counting and looking for the longest chain, this is atom carbon number 1, number 2. Here you have an atom of carbon, that's number 3. This is carbon number 4, 5, and 6. So the alkane of reference is going to be hexane. But because this is an alkyne, we need to change the ending, the suffix, from ane to ine. So we are going to have hexine. Then we need to specify the location of the triple bond. So we have 2 potentially starting points. We could start numerating from here, or we could start numerating from the other hand, right? We are going to pick this as origin of numeration because we have a substituent that is a methyl here. So by starting from that position, the triple bond will start at carbon 3, and the substituent would be in 2. If we start from the other hand, the triple bond would still start at 3, but the substituent would have a much higher number. So it's going to be 3 hexane. So we use the same approach that we use for double bonds. The number refers to the beginning of, to the atom of carbon where the triple bond is starting. And then we need to add the information that there is a branch to methyl 3-hexane. Now, we also learn that we also want to minimize, right? So in this case, it didn't really make, from the perspective of having a low number for the methyl, it didn't really make a difference. There was no conflict, that's what I'm trying to say. Like, this side, starting numbering from this side, starting numbering from here, would make a very small number for the methyl. So the numeration from the perspective of the triple bond was really equivalent. Either side was giving the same result, so there was no conflict. What if there is a conflict, like here? So if I start numerating from, so the longest chain here would be 1, 2, 3, 4, and 5, right? So I have a chain of 5. Now, if I start my numbers from here, this methyl group would be low, would be 2, but the triple bond would be 1, 2, 3, 4, 5. We start at 5, so it would be quite high. On the other hand, if we start numerating from here, the triple bond would have a very low number, 1, but the substituent would be 2, 3, 4, 5, right? So we can have it either way. We need to make a decision. So the decision is that the precedence, the yield, the most important one is the triple bond. So you pick the choice that gets you the triple bond to have the lowest number, even if that happens through the expenses of methyl. Okay. Now you can have the most unfortunate situation of having both a double bond and a triple bond in the same structure, right? Let's see these two examples. So the name of the compounds that have at the same time double and triple bond is Alkane, like crashing both, you know, in and ein in the same word. You don't have to remember that, it doesn't matter. But if you have to pick the name, and as usual, you're looking for the longest chain, right? So it's going to be, in both cases, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So for both is hexane. They're kind of flipped, right? They look very similar, but one has the double bond at the end and the triple bond in the middle. The other one, this one, has the triple bond and an ending and the double bond in the middle. Okay. So for the numbers, you start from the end that give you whatever appears first, either the double or the triple bond. You want that one to have the lowest number. So in this case, the one that appears first is the double bond. So it's going to be X. So you're going to give number 1 to the double bond and number 4 to the triple bond. And instead of writing like we did before, you see that now we put those numbers right attached to, so we could have write 1 hexene for ein, but because there are 2 bonds and so there can be a bit of ambiguous, we want the numbers right close to the suffix that they belong to. So 1 is the number for the double bond, I want it close to the prefix in, and 4, that is the number for the triple bond, I want it close to the prefix ein. Because here they are flipped, I will have that 1 is given to the terminal with the triple bond, and 4 ends up being the number for the double bond. So what I'm trying to underline is that it's not that the double bond has precedence or the triple bond or vice versa. You kind of want that the first one that's coming, it doesn't matter which one of the two, you want that to have a smallest number, unless you are in a situation that's ambiguous. Okay, so if you end up with the same result, like here, if I start, let's put some number. I don't know why my mouse is acting out. Okay, but maybe I got it. So let's take an example. So let's start numbering from here, in which case this would be 1, and then the triple bond would be 1, 2, 3, 4, 5, 6. So here the chain is a chain of 7, right? 1, 2, 3, 4, 5, 6, 7. So this would be heptane. So if I start numbering like that, double bond would have number 1, and so they would be low, and then they would end up giving number 6 to the triple bond. If I start from the other side, I still get number 1. Let's make it red. I get number 1 for the first bond that I find. So it's really the same thing. So in which case I have to make a decision, right? And we want everyone to make the same decision, because there are these huge catalogs of organic compounds that you buy, and you need, to have unambiguous entries for each of those compounds. So what's going to happen here is the double bond take precedence. Okay. So you pick the numeration that leaves the double bond having the lowest number. So we are going to start from the double bond. So double bond gets the number 1, and the triple bond gets the number 6. The very last things are cyclic compounds. Okay, so you see a bunch of compounds here, and they get like neat geometrical shapes, like a triangle if you have three carbons, square if you have 4, and so forth. First thing that you may notice is if you count how many hydrogen there are per carbon, there are exactly twice as many. So because we close it in a circle, we kind of lost 2 hydrogen respect to a normal alkane. So what are the angles normally for these compounds? So a triangle, you can't really make it, you can't really do much with it. It's going to be 60 degrees. A square is going to have an angle of 90 degrees. You can try to bend it a little bit, but there's not really much latitude in that respect. Now, why are those angles bad? Because those carbons have an hybridization sp3, so the angle should be 109.5. And those two angles, 60 and 90, are significantly smaller. And that's a geometrical constraint. There's nothing there, there is no other shape possible. So what's going to happen is there's going to be a lot of tension. Those atoms are not going to be happy, and those cyclic structure are going to have very strong tendencies to break up and open. So those are relatively reactive molecule in the big family of hydrocarbon that are not very reactive at all. And in cyclopentane, you see that you have an angle of 108, that's the internal angle of pentagon, so that's going to be quite close. So this compound is going to be much happier. For cyclohexane, you would have an angle of 120. That would seem too much, but that's a shape that is flat. Right, and we know that the atoms have a 3D shape. So with an hexagon, you can kind of bend and fold a lot, and you can get to the actual shape that has molecule that have a cycle of 6 atoms of carbons is going to be this one, where basically you have this structure. So where these are in front and this one are in the back. Respect to the plane, and they can also flip, and you can see here in this animation how they can move respect to each other in order to achieve that sweet spot of 109 degrees. So you see that sometimes it's as the shape as in the drawing up here. So let me get the pointer. This shape here now is going to have it, and that's called chair. It's a bit like a garden chair when it's kind of flat. Or some other times, it may have a shape that reminds you more of something like that. And that's called boat shape. So there is an alternation between the two shapes. That's it. you don't really have to worry that much, but makes the whole molecule happier and more. So let's see how to name this compound. We need to identify which one is the main chain and which one is the branch, or in the case of a ring we call it substituent, and basically it's the bigger. So in this case we have a chain of 4, 1, 2, 3, 4, so that would be butane, and attached to it there is a cycle of 3. So being 4 larger than 3, this is going to be a butane that has a substituent as let's say a branch. So and it's in position 2, right? Because we're going to give number 1 here and number 2 here, so that the substituent has the lowest possible value. So this is going to be 2-cyclopropyl butane. But more often than so, and let's say this is the type of question you will get in the exam, more likely, the cycle, the ring that we have is going to be the bigger part of the molecule. Therefore, the naming is going to consider this the main chain, and the CH3 is going to be the branch. Okay, so we don't really need any numeration, so we can just say methyl cyclohexane, because having only one substituent is by default number 1. But if we have 2 substituents, then we need to tell how close they are to each other, right? So if are they like adjacent, or is that 1 carbon in between or 2 carbon in between? Okay, so again we have a cycle, a ring of 6 atoms, and then we're going to assign numbers, and so we want the numbers so that the 2 substituents have overall the lowest number. So it's going to be 1, 2, and 3. And it doesn't really make any difference if I start from the other method, because the 2 substituents are identical. So this is going to be 1,3-dimethyl cyclohexane. What if I have 2 different substituents, right? Because in this case, I could start counting from here. This would be number 1, and this would be number 2. Or I could start, no, I'm sorry, that would be number 3. Or I could start, there's an eraser, so I can do that. Okay, so that would be number 3. But if I start from the right, then the methyl would be number 1 and the ethyl would be number 3. Okay, so what's the criteria here? We go in alphabetical order. So the substituent that comes first in the alphabet, in this case ethyl, is going to have number 1, and the substituent that comes after in the alphabet is going to be number 3. There are further complications, as is often the case in life, but that's as much as we are going to cover. Okay, so that's all.